Good morning, everyone, and welcome to this panel. Dr. Sherwood Randall argued very convincingly for a radically new grid, and one that must necessarily involve the increased reliance on cyber infrastructure. This reliance naturally raises concerns about cyber security of the grid, which is the main subject of this panel. So we have four distinguished panelists with us today who are all experts in this field. Details of their accomplishments and qualifications are found on the meeting website, but I'll introduce them briefly here first, after which each will give a short presentation discussing their thoughts on this topic. Then we'll open up the floor to questions from the audience. So let me now just briefly introduce each of our panelists. Dr. Annaswamy is the founder and director of the Active Adaptive Control Laboratory in the Department of Mechanical Engineering at MIT. Her research interests span adaptive control theory and its applications to aerospace, automotive, and propulsion systems, as well as cyber physical systems such as smart grids, smart cities, and smart infrastructures. She currently leads a very large and very active research group in these fields. She's received many awards, including being elected as a fellow of the IEEE and as a distinguished member of the IEEE Control Systems Society. She's also been an activist in the broader community, currently serving as a member of the National Academy's panel on modernizing the U.S. electric grid, on which we serve together, and also as president of the IEEE Control Systems Society. Our second panelist is Dr. Prateek Mittal, one of my colleagues here at Princeton. He's an associate professor of electrical engineering here. His research aims to design secure and privacy-preserving systems. A unifying theme of this work is to manipulate and exploit structural properties of information and network systems to solve security and privacy challenges facing our society. He's received a number of awards for his work from organizations ranging from industry to government and academia, and regularly serves in editorial and organizational roles for several of the leading forums for airing of work in cybersecurity. Dr. David Nicol is the Herman M. Dieckamp Endowed Chair of Engineering at the University of Illinois at Urbana-Champaign, where he's a member of the Department of Electrical and Computer Engineering. He also serves as director of the Information Trust Institute at Illinois and the director of the Advanced Digital Sciences Center in Singapore. Prior to joining Illinois in 2003, he served on the faculties of the computer science departments at Dartmouth College and at William and Mary, and he has won recognition for excellence in teaching at all three of these universities. His research interests include trust analysis of networks and software, analytical modeling, and parallelized discrete event simulation, research which has led to the founding of a startup company, Network Perception, and as his election as a fellow of the IEEE and a fellow of the ACM, the Association for Computing Machinery. Last but not least, our fourth finalist is Dr. Martin Otto, who has been a researcher and research manager with Siemens Technology, Siemens's central R&D organization, since 2005. He's held positions both in the US and in Germany, among them as global head of the Siemens Computer Emergency Response Team, and is currently head of the research group Cybersecurity Service Innovation at Siemens Corporation, Siemens Technology here in Princeton, where his mission is to provide Siemens business units with technology solutions and innovations that enable Siemens to provide state-of-the-art security services to customers. A special focus is on helping Siemens customers that operate energy systems and other parts of the nation's critical infrastructure to detect, react to, mitigate, and otherwise defend against cyber attacks. So as you see, we have a very knowledgeable group of experts here today, and I look forward to hearing their thoughts on future grid security. So now let me turn over the podium to Dr. Annaswamy for her opening comments. Anu?
Thank you very much for the kind introduction, Vince, and thank you very much for inviting me to speak at this panel on such an important topic. I could not have asked for a better introduction than what has happened so far with the comments that Dr. Sherwood Randall made earlier today. This is a hugely important topic, not just for the country, but for the planet. And what we really need is to understand how we can design ways in which we can ensure cybersecurity. And this problem really has been set in stage, if you were to look at it through centuries where we have made progress. Starting way back from Industry 1.0, we've had mechanization through steam and then through mass production with electric energy, with the advent of computers. And now we are at a stage which is coined as Industry 4.0, as a one where we require customized digital transformation. And this really is something that is set in motion because of a sustained effort in science and engineering, where several different technologies have come together. And this says that information can be processed even though we might have a very, very complex system, large-scale system that we are trying to understand and actually manipulate. And we have the ability to not only collect information, but process them and act on them at places that we need to. And all of this basically gives us an opportunity to really design very powerful large-scale systems, but at the same time, it also makes the system vulnerable to various kinds of cyber anomalies. Now, the problem that we have is the design of an electricity grid, which is an engineering marvel. And just in the United States, we understand as to how complex it is when we start looking at the numbers in terms of the miles of transmission lines that we have, a tremendous number of generation, commercial, both commercial as well as in utility scale. But what is really happening is that the grid of the 20th century is changing enormously, mainly because of issues motivated by sustainability, motivated by climate change. And so we really have more and more renewables. We do have more visibility. Many of the loads in terms of demand response that was mentioned earlier is giving us an opportunity to act on information and move the grid towards a reliable and resilient entity. We have an intelligent edge, which basically is the one that is causing this huge shift in the paradigm. And we have a very, very dominant cyber component with billions of controllable nodes, which really is the one that is introducing this huge challenge of cybersecurity. And this is not just empty statements. We've seen it again and again, actually most recently in 2015 and 2016, where attackers gained remote access to key points in this complex large-scale system. And we can bring it home by starting to look at what kinds of tools are available and what's our understanding. Cybersecurity is not a new topic. It's been actually explored quite a bit in the context of computer science. And cybersecurity is something that we understand from in the form of what is known as a CIA breach, which is that confidentiality is compromised, integrity is compromised, and availability is compromised. And all of this basically from a defender's perspective can be viewed as something that chips away at signal security or signal fidelity or timely access to the information. Or you can look at the whole thing from an attacker's perspective in terms of either eavesdrop, which is a disclosure attack, or corruption of signals, which is deception. And finally, the most malignant one, which is that it's a disruption attack. And in fact, you can look at some of the well-known attacks that have occurred in using this as a three different axes, if you will. And if you were to go back to the Ukraine power grid, interestingly enough, it's a combination of all of those different components. First, there was a disclosure attack through an attack that was through actually phishing emails and malware, and which was then followed by an integrity attack of deception, and finally a disruption attack, which basically compromised firmware at key vulnerable points. And so this in turn led to several customers left without power and actually had a very long-standing impact on the Ukraine power grid. So what all of this suggests is that if we really want to have autonomous decision-making in real time and have the sustained effort of a program, we need to make sure that these attacks that could occur either at the sensor level, at the information gathering level, or at the decision-making level have to be appropriately understood, and we need to develop cyber-physical security. And And there is no one silver bullet in this thing. We really need to look at this problem from a multiple concerted point of view and from a systems point of view. Because if you have an attack, one thing one could do is basically delay the effect and make the onset of attack affect the system rather, to be later and later. Or you could look at it from the point of view of ensuring that the maximum attack is contained, and that gives you some sort of a resilience knob, if you will. Or you could basically try and recover from the attack by simply detecting the presence of the attacker and recovering fast, making the recovery time faster. So ultimately, what we really are talking about are different ways from a systems perspective, or maybe even a system of systems perspective, to figure out how you can reduce the central region. So one example, for instance, and this was sort of a worst case scenario that was presented, where there are some actuators that are attacked. And what you do is basically make sure that that effect is not really manifested in terms of what you're measuring by having the sensors attacked as well. And the details, technical details are all in here. But what's really important is that the attacker basically has complete control of what's happening. And in this particular case, the example that they looked at was an aircraft, but you can replace the aircraft, which is also a safety critical system, say with a power grid, and we could have the same kind of a scenario. So basically what they argued that an attacker could do was that whatever you propose as a metric that says, okay, this is the goodness of the performance, is basically continuing to manifest the same kind of a signal, and therefore you're not able to distinguish, and therefore the attacker is stealthy. So in order to make the attacker reveal themselves, we developed this concept of baiting, basically where you deliberately introduce some false model, and the false model basically causes the shift into the residual, which is the quantity that we are monitoring. And that reveals the presence of the attacker. And so if you were to have no attack, you have a very healthy system. The stealthy attack, however, basically causes the actual signal to remain below the threshold, whereas that signal basically it becomes larger in the presence of the bait attack. So this is one kind of an approach. Another kind of approach is something that is based on resilience, where you could have a repeated broadcast and you basically leverage the fact that you have a very strong cyber presence, and you can repeatedly basically broadcast the signal and do some appropriate processing. And that processing basically gives you, so here's an example where we showed that this resilience-based solution, this is a power grid problem where you have a wide area network, and this actually is how power is actually interconnected across the nation, that by processing it using the information in the kind of repeated broadcast, we actually were able to make sure that the attack did not really debilitate the grid, but was able to actually bring it all together. So the main point that I want to do is present here is that this is a fantastic opportunity for the scientific and engineering community to really have this nationwide manifest, if you will, and develop systematically how the power grid can be made secure. And given that there is a strong cyber presence, and given that the grid is basically being turned around and made, and the edge is becoming more and more intelligent, we really need to address the problem by looking at it from several perspectives and ways, and that's exactly what we are actually doing in a project that we just started with my colleagues Vincent, Prateek, who are the part of the panel. So thank you very much, and it's a pleasure to share my thoughts with you, and I look forward to further discussions.
Thank you very much, Anu. Very interesting remarks and a very compelling argument for taking a holistic approach to the problem of cybersecurity in the grid. So now let's turn to our second panelist, Dr. Mittal. So Prateek, would you like to share your thoughts with us?
Thank you, Vince, for inviting me to today's panel. I will discuss how an adversary can exploit an Internet of Things botnet, which is a large collection of compromised IoT devices, to disrupt the operations of the power grid. I'll begin by highlighting the conventional perspective on attacks against the power grid, which involve an attacker targeting either the physical infrastructure of the grid, such as generators, or its control center, such as the supervisory control and data acquisition, or the SCADA system. Now, there have been many instances of an attacker hacking into the control units of the SCADA system and using this to disrupt grid operations. And the attack that Anu described in the previous panel presentation, targeting the Ukrainian power grid in December 2015, is a fantastic example of such an attack. In this presentation, however, I want to make a case for a new type of cyber attack on power grids, which does not involve the attacker targeting either the grid transmission infrastructure or the SCADA system. Instead, the attack relies on a collection of compromised IoT devices. Such attacks are feasible because IoT devices have not been designed with security and privacy properties in mind. And in this talk, I will present a case study of disrupting power grid operations by leveraging malicious IoT devices. This talk is based on the two papers that I'm listing in the slide below. These are joint works with Saleh Soltan, who's a former postdoctoral scholar at Princeton, and Vince, who's moderating our panel today. Now, a collection of compromised IoT devices or an IoT botnet can have consequences that go much beyond individual security or individual privacy violation. And a really famous example of such a botnet is the Mirai botnet, which consisted of around 600,000 bots. And an adversary used access to the 600,000 bot devices to launch distributed denial of service attacks against DNS servers all over the world. And this attack was one of the largest of its kind at that time. Now, let's see how such IoT botnets can impact grid operations. Now, a common assumption in many previous security efforts on the power grid has been that the power demand can be predicted reliably on an hourly and daily basis. And this prediction is made using historical data and weather predictions. However, with the growth in the number of high wattage IoT devices, such as air conditioners and heaters, is this still a safe assumption? Notice that different from previous attacks, the threat vector here is electricity consumers and not an adversary that's directly trying to hack into the control system of the units. So let's try to imagine a concrete IoT botnet of high wattage devices. And to make that visualization easier, we're listing some of the most common high wattage IoT devices and their power consumption on this table. So towards the top of this table, we see air conditioners, which can consume up to 1 kilowatt of power. And towards the bottom, you're seeing electric ovens and water heaters, whose power consumption can be on the order of 5 kilowatts. Now, if we take the number of bots in the Mirai botnet, which was 600,000 bots, and we multiply it with the power usage of electric water heaters, we can see that an adversary with a Mirai-sized botnet of water heaters can instantly change or manipulate demand in an area by 3 gigawatts. Now, this is similar to an adversary having access to some of the largest currently deployed nuclear power plants. So think about the consequences of an adversary having the ability to manipulate power demand at this scale. And indeed, based on this observation, we identified the concrete attack strategy that an adversary controlling an IoT botnet can use to manipulate the demand in the grid. And the idea is that an adversary that controls a sufficiently large number of such compromised devices can synchronously switch them on or off. The advantage in synchronously operating these devices is that this can result in a huge imbalance between demand and supply, which can lead to generation failures as well as line failures in the grid, eventually leading to the possibility of large-scale blackouts. Now, let's see some key experimental results demonstrating the threat of such mad IoT attacks. Now, a sudden increase in demand through this IoT botnet results in an imbalance between demand and supply. And this imbalance can result in a sudden drop in the frequency of the power system. And the magnitude of this frequency drop depends on the inertia of the system. If the frequency drops below a particular threshold value, it can result in the tripping of generators and blackouts. So for example, using simulations on the Western Systems Coordinating Council bus, we showed that a 30% increase in demand results in the tripping of all of the generators in our simulation. And such an attack would require access to about 90,000 air conditioners in a geographic region. Now, an imbalance in demand and supply can also result in line failures because of the grid operator losing control over power flows. Now, this can have a cascading effect, resulting in a cascading series of line failures. So for example, we showed via simulations that a 1% increase in demand in the Polish grid in 2008 initiated a cascading line failure, resulting in 263 line failures and 86% outage of loads. And such an attack required access to about 210,000 air conditioners. In summary, due to the increasing number of IoT devices and their insecurity, it is critical to think about threats that arise from a collection of compromised IoT devices. Our work has shown how they can cause large-scale blackouts based on manipulation of demand attacks. And these observations motivate the design of countermeasures that protect the grid against the IoT botnets. I will conclude by emphasizing that the threat of IoT botnets is not just limited to manipulation of demand attacks. So for example, our previous panelist, Anu, showcased the exciting vision of leveraging information from the grid edge, including IoT devices, to enhance grid situational awareness, operations, and control. However, we must keep security threats in mind while leveraging data from IoT devices. This is because compromised IoT devices could otherwise provide bogus data as an input. And then if we perform autonomous decision-making, including machine learning on that bogus data, it could lead to catastrophic failures. Thank you.
Thank you, Prateek. Very interesting and a little frightening, but very interesting to hear. So now let's turn to Dr. Nicol. Dave?
Right. Well, thank you all for inviting me to this this meeting. I found the presentations made so far really very, very interesting. In the panel that we're in, we will have a third of talks that are talking about much the same thing, but with slightly different perspective and certainly different graphics. But with the previous panelists, I saw a lot of connection with what it is that I wanted to talk about. So thinking about the security challenges for a grid in transition, what I'm principally interested in is how we approach quantifying the impacts of these transitions and the impacts of security measures that we might apply. So I come to cybersecurity and the power grid through the door of simulation and modeling. Through a historical accident back in the 90s. I got pulled into cybersecurity, and I came along with a toolbox of systems models and analysis. And so I'm fond of models, and I think they can tell us rather a lot about what's going on. So as I'm thinking about how to approach what it is that I want to do, I'm going to use lots of models. And so here we have a model of a physical system, and you can insert many different kinds of physical systems that are in a graphic that's at this level. But think of a power grid, think of simulators of power grids, but also as we think about grids in transition, this picture can stay the same, but the models change as we migrate into more towards microgrids that are connected, for example. As we include more solar and wind, then they all get bundled into this model of a physical system. The physical system is affected by computers and communication. and they are done so through actuators. And so I've here boxes that are the actuators, and of particular interest, the actuators that can be reached through cyber means and impact the physical system through cyber means. And so that's obviously important. As we think about the security risks on the system, we're going to need to think about models of attacks on the controls. And there are models that we know about, where there are attacks that we can imagine and try to model. A big challenge are the attacks that we can't model or that we don't know. As someone said, you don't know what you don't know. And that remains rather a large problem. But we can go quite a ways in modeling the attacks through the actuators on the physical system, and we'll do that. Then there's the question of how does the adversary get to the actuators? And so we'll have models here of cyber-based control, and these models need to include the adversary. Might be an insider, it might be an outsider who gets access to the system through ingress. A lot of work has gone on in models of cyber-based control, and I think I'll say a little bit more about that. But as we go now to thinking about the models of cyber attack impact on the actuators, Prateek just presented one example, for example, and that had to do with cycling of breakers on the system when it had high consequences. There was a demonstration at Idaho National Labs in 2007, I think it was called the Aurora demonstration, where they cycled open and close commands to a breaker that sat between a generator and the rest of the grid, and that caused the generator to go out of phase and shake itself to pieces. And so one of the attacks that was demonstrated, and you can find it on YouTube to see the generator shaking and a bunch of smoke that they introduced for visual effect, because there wasn't actually any smoke, has to do with sequences of commands that are not expected in the system, and you might actually look for that. So another kind of attack would be cycling of commands. We see this in enterprise systems, but that could certainly cause bad things to happen here. Attacks that are based on corrupted data, attacks that are based on denying access from the operators in the control station to the actuators, or denying situational awareness, denying them the ability to see what's going on so that they can make informed decisions about what's going on. And of particular interest and concern are attacks that involve multiple actuators. The system, the grid is engineered so that it can tolerate small-scale failures that are anticipated. But it's not engineered to resist an attack that would be caused, for example, by corrupted firmware updates that are going into most of the protection devices that get deployed in the network, and the firmware causes a bunch of these breakers to do the wrong thing, all in coordination at some particular time. The system is just not engineered to deal with that. So we need also to characterize the intersection of the cyber and physical components. And so that means you need to look at the actuators and ask, what impact do they have on the physical system? Because we're going to be concerned about the impact on the physical system that attacks on the actuators have. And so breakers are going to affect the power flow topology that's going on. In more general physical systems, you can imagine pumps in there. If you have models of liquid natural gas, might be attacking pumps moving liquid or not. If your physical system is a ship, perhaps the attacks are changing the throttle on the engines and causing the ship to pull away from a connection to a liquid natural gas connector, or a robot arm that moves its arms and opens and closes. So, the point being is the attacks on the physical system are done through the actuators. And so the question becomes, what can those actuators do? What sort of attacks are possible? Because we're really interested in the consequences of those attacks and preventing them. Then there's the piece of determining what cyber access there is to those actuators, and you want to use as much information as you have. And so this model can be quite complex. It can be have representation of all the devices, or as many devices that you know of in the network. It can include access control devices like firewalls. It can include various sorts of key servers for cryptography that's going on. Here, what you want to do is put in as much stuff as you can to try and analyze it. But one of the challenges is that there are things in there that you don't know. And one of the research areas of some interest has to do with encapsulating or modeling uncertainty that's within this network model, to see what uncertainty you have with respect to how you can get to the actuators and what it is that you can do. So that's yet another model. And then so finally, not quite finally, we're getting close to finally, we're interested then in, you say, well, all right, suppose that the adversary has root access to this device, has user access to this device, does not have access to this device, these two devices. What attacks are possible from that? What damage can be done if you tell me what actuators are compromised and how it is that they get compromised? So, given all these models, we can ask the question of how do we go about analyzing the adversary's ability to get to these actuators and do bad things. So there's a well-developed literature, actually an industry, in developing what are called attack graphs that model the network, that model the adversary's ability to get around in the network and get to those actuators. And so, a question is, what do you do if you have an attack graph? Many analyses will say, well, we can use the quantification, we can use edge weights and so on, and identify what the easiest single attack path is for the adversary, and use that as a measure of how well protected the network is. But I ask the question, what makes us think that the attacker can find the easiest attack path, or that the attacker would use the easiest attack path? Because the attacker does not have complete knowledge of the network, whereas a shortest path algorithm does. So you might say, well, all right, what we'll want to do is analyze the number of ways that are presented to the attacker to get to those actuators. And so maybe what you want to do is enumerate the number of paths that the attacker has available. And I'll ask the question, well, okay, suppose you do that, and suppose that you can put some controls in your network and reduce the number of paths from adversary to actuators from 10 million to 1 million. So are we 10 times safer? I'd say no. There's a funniness with that metric. Maybe you can take the logs, but still, we need another way of thinking about it, I think. Or so maybe what we want to do is look at associated cost with every path, and look at some distribution that you can measure at the actuators and do some analysis there. And that's better, I think. But one of the things that's missing throughout all of this is analyzing what the consequences are and reasoning backwards. And so in reasoning backwards, or reasoning perhaps the right way, is if we look at the physical system and say, what are the possibilities that have the most costs to us? What are the ability of the attackers to get to the actuators to cause these kinds of attacks to happen and inflict these sorts of costs? And that takes us into a different realm of analysis involving cut sets and asking the question of what it is we should modify in the computer network to completely thwart an attack. And this is the last slide, I believe. And so the idea there is to be looking at the things that we want to avoid having happen in the physical system, ask ourselves, what actuators need to be compromised to cause that to happen, and then look at the network model and say, if I were able to patch this particular vulnerability, if I were able to resegment the network and put in a new firewall, then how do I cause that attack not to be viable because it denies access to the adversary of a particular actuator? And so with that, I'll leave it just to say that, I think that the problem of thinking about security challenges for the grid in transition, you need to come at it in some kind of holistic way, a system level way, and in a way that's not tied to the technology itself, but is able to itself adapt as the technology changes by changing the models of the technology.
Okay, Dave, thank you very much for those insights into how the structure of the grid relates to its security. And now, last but not least, let's turn to Dr. Otto for his opening remarks. So, Martin?
Yeah, thanks a lot for the handover, and thanks a lot for having me today. So, being the fourth with my pitch in a row today, I asked myself, how can I avoid redundancy? So I thought, let's approach that a little bit from an operator's perspective and look at secure operations. So we know, for the question base is, what do we need to do to have a secure smart grid? And it's basically the same task that we know from IT. So first of all, we need to build a secure system. And it comes with challenges. First, you need equipment that can actually be procured, that can be bought, that supports our features interoperably, and can also be configured securely. Then you need knowledgeable staff to actually do that secure configuration. And then, of course, you also need to configure it according to standards. And here for us, the most important one, of course, is NERC. So once you're successful in building a secure system and you deploy it, 10 seconds later, it gets attacked. So now your challenge is to keep operating it in a secure state. And the typical challenges and tasks that you have to look for here are the three on the bottom right. First, you want to provide continuous transparency via testing. So vulnerability scanning, penetration testing. From time to time, you need to check if your assumption about the security posture still holds. And if not, you need to act. You need to constantly adapt to maintain a secure state. So this means various things. Patching when the products that you're using have known vulnerabilities. It means changing your configuration if the current configuration no longer provides the security level that you want to have. And it goes all the way down to crypto agility. And the last part, of course, is monitoring and attack detection. Because if you have no means to find out when you have an attacker in your system, you cannot contain it, you cannot prevent damage. And for all of that, we need data. Unfortunately, data is at the very heart of smart grid, right? Given the challenge that we have in smart grids, the distributed energy resources, the fluctuating generation of renewable energy resources, and the demand to achieve much higher degrees of efficiency in order to control climate change. All of that requires that we have more data that we can analyze so that we can properly derive actions and enact much more granular control on the entire system. And that requires data, and data requires connectivity. And unfortunately, that comes with a price, because higher connectivity usually means more attack surface. So how do we deal with that? Fortunately, we know a lot of prior solutions from IT. So how easy is it now to take what we think we have as solutions in IT and apply them to operation technology? And one big challenge, of course, and that had been mentioned before, is that in operation technology, availability is king. It's not the only challenge, but it's the root cause of a lot of these challenges. So in the next 5 minutes, I want to dive a little bit into the 4 challenges that I have here on the slide, and I'm going from left to right. So the first challenge is installed base. So here, the challenge is that the energy industry, the operators typically have a traditional, the conservative mindset with innovation cycles that are measured in decades. And don't get me wrong, that isn't necessarily a bad thing, because the fact that utilities are somewhat risk unfriendly, basically, is the main reason why during our event today, our lights don't flicker. But it also means that there are devices in the network that we usually refer to as brownfield that are operated for decades. And the picture that I've brought on the top left is such an example of a control system that was built in 1971. And when this picture was taken in 2018, it was still operational somewhere in Myanmar. So that means all solutions that we think about to increase cybersecurity in smart grid needs to take into account that we have a significant installed base of aging equipment that sometimes predates the internet, and it doesn't have the computing power that we might want to have in order to deploy advanced features. And of course, this is met with a mindset that comes from IT, where you're used basically to throwing away your phone every 2 years because it's outdated, and that's driving a lot of the smart features and the features in smart devices and the whole topic of IT-OT convergence, but which makes it difficult to apply what we know from IT in the OT world. The second challenge is assurance. So as I said, from time to time, you want to check your security posture, you want to do scanning and maybe penetration testing, but you need to do it in a way that it guarantees availability. If you cannot guarantee this availability, you will not be able to do it in flight or in production. And only doing it during maintenance outages just doesn't give you the full picture. So that requires better solutions than we currently have. And of course, it also needs to take care of the other challenge that we have, like need to highly automate it to deal with the bandwidth issues that we have of like thousands of substations that may be located in remote locations and so on. The next challenge is patching. And we know that patching is still a challenge in IT. It has been a challenge for decades. We're now at a level where basically patching makes us comfortable in IT. So it doesn't happen very often that operating system patches break your system, but it's also not unheard of. So in OT, that unheard of is a problem because here patching must not create availability risk. So what we can do here are two things. Well, the first, non-brainer, of course, is increase patch quality. So better trust in the patches so that we can apply them during production. And I think the second thing where we're not that good at yet is increase resiliency to bad patches. So if a utility can patch devices during production and can deal with the fact that maybe an occasional bad patch causes availability issues and that risk is low, then all of a sudden it enables us to actually patch during production, which is what we need to make sure that we don't have the attacks happening. And of course, you also need easy asset inventory handling, which is still a big problem in both IT and OT, because you need to know what you have in order to know what and when to patch. And the last challenge is attack detection. So attack detection is basically, you basically have three main ways of how you can address it. The first one is pattern-based, using threat intelligence. So just seeing if you can find the same indicators of compromise in your logs and then act on it. The problem here is that data is actually scarce. There's very little genuine OT threat intelligence. And when you think about it, that's a good thing, right? Because it means that we don't have a large number of successful attacks on the energy system yet. So we're quite lucky there. But it means it's not a very effective way currently to detect attacks. Second approach is using artificial intelligence, machine learning, and that has proven very, very successful in giving us a lot of insight into a myriad of topics, so also in attack detection. But if you're using supervised learning, you need labeled data. You need a bucket of data that contains samples of known malicious activity and the bucket of data that contains samples of known benign data, right, benign activity. And both actually is pretty difficult to get by in practice, making development and testing of new approaches actually difficult in practice. And the last part is anomaly detection. So basically, if we can't do supervised learning, then let's just establish a baseline and then declare anything that is deviating from the baseline an anomaly that is a potential indicator of an attack. Now, the big problem here, and we know that from IT, is that the price that you pay for that is typically a high rate of false positives. And OT should provide us better means to bring this false positive rate down, because OT is much less heterogeneous than the IT environment. So if we find better ways of injecting domain expertise into these detection algorithms, it should help us significantly to improve our detection mechanisms. So overall, my takeaway basically is that we still face significant challenges to build a secure, solid base in smart grid. And all the advanced features that we want to have require a solid, secure base to successfully bring in their benefits. And that is still a challenge. And those are my 2 cents. Thank you.
Thank you very much, Martin. Very interesting and a very comprehensive view of the things that need to be done to deal with cybersecurity in the grid. So now I want to turn, if I can, to some questions from the audience. And we have about 10 minutes officially, or 11 minutes, and I've been given permission to go 5 minutes over because we have a lot of really, really interesting questions. So let me just get right to that. I want to start with a very basic question that came from an audience member, which I think is perhaps I'd like to hear your thoughts on that. And so what are the motives of cyber attackers on the grid? We talked about the attacks. We didn't really talk about why people might want to attack the grid. Does anybody want to address that?
Sure, I'll take a whack at it. I'll say the same things, or others will probably say the same things I would, so I'll go first. You take something like the Ukrainian attack. I think that was making a point. So there was some outages for a while, but they didn't destroy equipment. The attack that followed a year later demonstrated that they had gotten better at it, but they weren't trying to destroy things. They were trying to make a point. We have to be nation states as they get in will sometimes be making a point also, particularly if they get in and we find out that they're a small country, shall remain unnamed. There are a couple of them that have been able to get into our systems. The larger players would be leaving things behind in preparation for the big one if it actually goes hot. So just sort of laying in wait. And then one last possibility, and I'll turn the talking stick over. We haven't seen yet, but I expect sooner or later, and that would be ransomware. And so someone would actually be going and trying to get some money out of this. If you don't pay us, then we're going to destroy things.
Oh, great answer.
Yeah, and I want to maybe add to that. It's really the entire spectrum, right? If it is easy to attack something, script kiddies may just do it for fame and glory. If you can show that you did something to a utility, that in those circles is really fame. And then you have the cyber criminals. And David said about the ransomware. A utility, of course, is much more critical. So it should provide more opportunity for a criminal to extort money out of them. So that is a strong motivation for them to go after them. And then, of course, nation states, as David alluded.
Okay, thank you. Let me move. Oh, Anu, did you want to say something?
Very quickly, I just want to add, I think it's a very good question, and I think it's a very hard question to answer. And most importantly, I think it's something that presents us with a challenge that it continuously changes. So when you think that you've modeled everything and you say, okay, these are all the different motivations and so on, then comes a new one, which you have not looked at before. And so what it means is that when we try to develop tools for mitigation, we always need to sort of continuously make this a living document and a living architecture and build our defenses, because what you think of as models are no longer are the models in the next year and the year after and so on.
Okay, thank you all. So let me ask another question. Very good question is, how do we weigh the risks of cyber attacks versus the risk of not deploying cyber infrastructure? So for example, cyber infrastructure, one of the reasons is to mitigate issues such as contribution to climate change, which is another type of risk. And in exposing the possible security issues that we're disposing, are we putting a chill on the deployment of cyber infrastructure? That is, are we scaring off the public from these kind of things? I wonder if anybody has that.
Yeah, maybe I could respond to that. I think the first point I want to make here is that it's not the case that you can either have security or you could have functionality. I think in many real world deployments, it's possible to have interesting functionality in a system while providing security and while providing privacy. I think the important thing to keep in mind is that the system security community should work together with the power utility company. Otherwise, if we have grid utility operators deploying new protocols in isolation that don't have security and privacy properties baked by default, then we are at a significant risk of catastrophic failures due to attacks.
Yeah, good. Any other thoughts about that?
So I'll take a whack at that. So colleagues of mine have done work that balance the risks of patching versus not patching, right, in an operational technology environment. And so there's a mathematical framework, and you can approach it mathematically as an optimization problem. And that's fine, but it doesn't really get to the question that I think was being asked, and that's weighing the larger scale issues that have to do with applying security or not applying security. And one of the challenges there has to do with the fact that the infrastructure is largely, completely owned and operated by private industry. And so there are a number of things that the industry has to be motivated, incentivized, or not decentivized, to do things to provide the security. And it really comes down to whose problem is it? And so if you look at the problem from the point of view of a particular utility who might do something, they're going to have certain motives and objectives that have to do with them. But the problem that we're talking about is much wider than that. So how do you incentivize people to work together to deal with these kinds of questions?
Okay. Other thoughts? Anu, yes.
I think that the opportunity that we have is that a continuum of solutions. I think that there is a whole host of alternatives between no security and security. And the fact that we can provide a multi-pronged solution approaches and a whole host of systems-based solutions suggests that there are many alternatives for a given scenario. And there's definitely no one silver bullet. And therefore, I think there are many gradations of security one can offer that is appropriate for a given situation. But that requires a sustained and concerted attack by this, sorry for the use of that word, by the scientific community at large.
I just think we don't really have the choice, right? I mean, we need the features and the functionality and the benefits that the technology and the connectivity in smart grid gives us, because otherwise we will not achieve even the basic targets. And it's 2020, right, or the 21st century. We can't deploy this kind of control technology without proper security. So we actually don't have the choice to say we do either or. We can talk about what's the right level, what is the right risk that we assign to certain threats, and what is the right level of protective measures, but we really don't have the choice to do either or.
Okay, thank you all. I want to just add a point of clarification here. Maybe I'll ask Dave just quickly to address this. A couple of audience members have asked the question, what is a patch? I'm not sure everybody knows.
I'm sorry. Yeah, no, okay. So when you have software that has a flaw in it that can be exploited by an adversary to do bad things, then a patch is a way of changing that software, slapping think of a hole in a boat and slapping a patch in a hole in the boat, and that's what happens.
Okay, thanks. Yeah, I just want to clarify that. We have so many good questions, but let me get to another one. Wouldn't a major push to dramatically increase the number of microgrids make sense? So if there's a major cyber attack on the grid system, necessary businesses, emergency responders, et cetera, could still continue to operate. Any thoughts?
Yeah, I think there's this idea that part of the ideas on how do we get the grid more resilient is to make sure that something happens that it kind of the effect can be contained. So it can be drop down to a dumb grid, or it can drop down to a lot of different microgrids that can still operate without the overall connectivity. All these are approaches. So the question is how realistic are they, and how much benefit do they actually get us? I don't think that verdict is out yet.
Good. Any other thoughts about that?
Yeah, I think that's a great point. This is something that is being addressed by the grid and cybersecurity community at large, and really approach the use and the analysis and synthesis of microgrids and clusters of microgrids as points of resilience. It will require a lot of careful study, and it will also require not only this engineering community to look at this problem, but all of the policymakers and regulators to allow microgrids to be basically support structures, because it's really flipping the grid inside out and have a bottom-up solution rather than a top-down solution, and really not have the infinite grid come in the way of the microgrid supporting. So I think this is a very important point, and I think something very relevant for national security.
This sounds like a great idea. I think one challenge I just want to highlight is that the actual protocols that are used for these microgrids to interface with the grid operator or between each other still need to be carefully designed with security in mind.
Thank you for saying that, because right now they aren't. And so we're at the University of Illinois doing some work looking at microgrids and worried about these kinds of protocols. And from a security point of view, it's increasing what we call technically the attack surface. You're adding more complexity to systems, you're adding more points where an adversary can come in and do things, but the structure of it means that the impact of that might be less. And so there's a trade-off that exists there. There's a disadvantage to microgrids, I think, and that is that they aren't, in the aggregate, as efficient as a centralized system. One of the things that you do in the power grid is you're able to generate power here and inject it into the system, and in some flow sense it's used elsewhere, but there's inefficiencies that incur. So it's a great question, and I think we're going that way, but there are a number of problems along the way that have to be solved.
Okay, thank you all. Let me shift gears a little bit. Here's another very interesting question. So what steps can ordinary citizens take to increase our national resiliency to cyber attacks, especially related to the energy grid? Any thoughts on that? Yeah, Dave.
Write your congressman. It's not a technical problem. I mean, from a user's point of view, I don't see that there's a technical problem or a technical thing that you can do to cause great change, but it's a political problem.
Yeah, I think the only technical thing that individual consumers could do is basically make sure that you are on top of things concerning vulnerabilities and patching of whatever devices you have at home. Right? I mean, the IoT example that Prateek presented is I think a prime case for that. If your Alexa or if your electric heater is vulnerable to an attack and it's connected to your Wi-Fi, that enables IoT-based attacks. It is difficult for the average consumer to do that. That is the big problem that we have. But at least that's on a technical level a little bit that can be done.
Yeah, following up on Martin's question, response, as we all know, the electric utility industry is very heavily regulated in this country, I guess all around the world for that matter. And does the U.S. have the right regulatory structure to promote the kind of cybersecurity we need in the future?
Oh my goodness. You have to have a whole seminar on that particular topic.
Maybe this is the wrong group, but I just, it is a big issue, right? And Martin just pointed it out.
It is a big issue. I'll just say two things, if I can remember them both. One is that in the existing regulatory structure, you're talking about compliance, and compliance does not equal does not equal security necessarily, and so that's a challenge. The other is that there is a great deal of pushback from industry on this. I think the challenge there is to find ways of viewing security so that it's seen that this is not just a drain on resources, but somehow makes a better system. People talk about return on investment, and that's sort of simplistic, but what incentivizes industry to deploy security, and that remains a challenge, I think.
I would say even outside the context of the grid infrastructure, I think regulations in the context of security and privacy have been very, very challenging. I think just relating to David's point, it's so hard to quantify notions of security, right? That often we see that even security-oriented products actually don't compete on security; they compete on functionality and features, right? We're starting to see some success in the privacy landscape with regulations like GDPR. But it's easier to put in place those regulations because they connect directly to users' rights, privacy rights in particular. It's harder to do that for security.
Yeah,
I actually remain extremely optimistic on this front. I mean, having listened to hundreds of meetings and panels and conferences and so on, what used to be sort of like a little buzz with renewable penetration 10 years ago is now sort of a bullhorn message right now everywhere. Similarly, cybersecurity and the efforts taken by regulators and utilities and so on used to be sort of on the periphery, but now that too is becoming a very central message. In fact, there was a meeting last few days where so many different communities came together, researchers and entrepreneurs and utilities and regulators. And in all of those cases, the underlying theme that I heard was cybersecurity, that we really need to understand how we are going to transform the grid at the edge. And for that, we have to protect this vulnerability. So it's not just us, the scientific community, trying to make a change. All of the interested stakeholders in this conversation are at the table and they're ready to start this conversation. And I think that we will have some really good solutions that can be implemented on this canvas. I'm very optimistic, actually.
Okay. On that note, we've already imposed. Thank you, Anu. On that note, since we've already imposed on the audience for an extra 5 minutes, I think we have to cut this off. Although looking at the Q&A, there's so many other interesting questions. I'm sorry we can't just keep going. But let me take this opportunity now to thank all the panelists for their presentations. These are really great. Thank you for your answers. Thank the audiences for your questions. And I'm sorry to those of you whose questions we couldn't address. All of them look very, very interesting. So thank you all and goodbye. Enjoy the rest of the conference.